goes. Okay. Again, last part of 1-4 here. Still talking about continuity a little bit. Directions are just going to be a little bit different today. So here we go. Part 4. Starting out, this is what we're supposed to do. It says discuss the continuity. Discuss the continuity of the function on the closed interval. Discuss the continuity of the function on the closed interval. We've had intervals before. Closed interval means it has brackets. Open intervals have parentheses. So remember, if you have a bracket, if you have closed intervals, then you can equal those values. Okie doke. So this is the first one. And again, our calculator is going to be helpful today. Number 1 says f of x equals the square root of 25 minus x squared. Now, that's important, obviously. That is our function. But this is just as important. You're only looking at what's going on between, and I'm going to point this out real quick here. Anytime they give you an interval, these are your x values that you're supposed to focus on. We are only focused on the x values between -5 and +5 and equal to -5 and +5 since there are brackets. So once we get this graphed, when you look at the graph, which is going to be our next step here, I'm typing this into my graphing calculator. It was the square root of 25 minus x squared. I'm only supposed to look between -5 and +5. Now, it turns out on this graph that those are the only values where the function exists anyway. It only exists between -5 and +5. So it's not always going to be like that, but this is what you're looking at. Everything between -5 and +5 and equal to -5 and +5. Now, I don't see anything up here that looks suspicious. I don't see, like if you go back to the function, it was a square root, but it was not a fraction, so I don't have to worry about any x values making the bottom equal 0. I don't see any asymptotes. I don't see any breaks in my graph. I guess the only x values that I might be concerned about are -5 and +5, because my calculator is not really giving me a good picture of what's happening right there. So if you want to trace to -5, you get back a y value, so there's not a hole there, there is a point there. Same at +5. There is a point where x equals 5. So I would say on this first example that this function on that interval is continuous everywhere. Now, I guess since they gave us an interval, we might want to be careful about using the word everywhere. Let's go ahead back and say specifically that it's continuous on the interval -5 to +5. That was what we were looking at anyway, but if we say continuous everywhere, it might seem like it's continuous for all x values. It's only continuous for those. Okay, now we're going to try some more here where there might be issues. if you look at example 2, it says f of x equals 2 over x squared minus 9. And I'm only looking, again, these are x values. I'm only looking between -1 and +3 and equal to -1 and +3. Now, before I even graph this, I'm going to do kind of like what we did yesterday. I want to think about my suspicious x values. If you think about that equaling 0 and you solve it for x, you should be concerned about +3 and -3. Now, actually, there's one of those that we don't have to be concerned about. Anyone know which one I don't have to worry about? -3. Why don't I have to worry about -3? Yeah, it's not even in the interval. So the only x value I'm concerned about really is x equals 3. I want to look on my graph and see what's happening at x equals 3. So you got to be careful about your parentheses. 2 divided by the quantity x squared minus 9. You have to put parentheses there. Again, I'm looking at 3. I want to know what's happening at x equals 3. So, 1, 2, 3, I can see pretty clearly from my graph that there is an asymptote at x equals 3. It is not continuous at 3. So, there's 2 different ways that you could write your answer for this problem. If you want to go back and use that interval, and by the way, I didn't show this very well on my graph, but you do want to keep in mind everything else in the interval. But we can see -1 all the way to 3. Everything else there is fine. It's just right there at 3 that I'm worried. Okay, so this is what you could say. You could say that the function is continuous on, I'm going to take that interval that they gave me and I'm going to use it, except for I'm not going to put a bracket with the 3 anymore. I'm going to put parentheses there because it's not actually continuous at 3. It's good for everything between -1 and 3, equal to -1, but you just can't equal 3. That was our point of discontinuity. Now, if you'd rather go back and kind of describe this like we did yesterday, you could also say that there is a non-removable, getting lazy here, I'm going to abbreviate, non-removable discontinuity at x equals 3. Non-removable because the limit would not exist there. I'm fine with either one of those answers. Now, I will say here in a little bit, the directions are going to want us to use intervals. So this might be the approach you want to start getting used to. But, I mean, it just said discuss the continuity. So that would be another way to discuss it. Okie doke. Any questions on example 2? Find the suspicious x values first. Now, directions are changing. They might change a couple more times here. Yes. This says, discuss the continuity of the composite function. We're discussing a lot today. Discuss the continuity of the composite function h of x equals f of g of x. This is fog here. F of g of x. So basically what we're going to have to do first is they're going to give us f of x and g of x, but before we talk about continuity, we need to figure out what f of g of x is first. So I'm actually just going to label this as a step. First thing you need to do is find f of g of x. They're labeling it h of x, so I mean you can do that too if you want. But what this means is take g of x, because we always start with the function on the inside. Take g of x, plug it into f of x. Okay, so instead of 1 over x, now it's 1 over the square root of x minus 1. Again, if you want to call this h of x, you can. That's what they called it earlier. So now we have to discuss the continuity of h of x. This is the function that we're going to type into our calculator. And this is the function where I need to find any suspicious x values. Okay, I can see right off the bat here that I'm a little bit concerned about x equals 1, because if it was 1, 1 minus 1 is 0, square root of 0 is 0, then you would be dividing by 0. So that's the one that I'm probably going to look at closely. Now, back to our graphing calculator. 1 divided by a square root symbol is kind of like a grouping symbol, so you probably don't have to put parentheses around it. I already forgot what it was. It was x minus 1. So doing it like that should be fine. If you have an 83 or something different, you might have some parentheses right there that you can end. But this should be good enough for our graph. Now we are discussing continuity. So again, there's a couple different ways you could word it. I'm concerned about x equals 1. If you trace to 1, you're not getting back a y value. My calculator might not be showing me everything here. This probably goes up forever and ever, and this is probably some kind of a vertical asymptote. So as far as discussing the continuity, I might say, I'm going to go back and use an interval here, because that is what we're going to have to do eventually anyway. I'm going to say that this function is continuous on, now think about where the function is at. The function starts at 1, but are we allowed to equal 1? No, so I would use parentheses right there. And it's going to keep going this way forever and ever. You can trace to all those x values if you want to, and none of those should be a problem. The only one I was worried about was 1. So I'm going to say continuous on the interval 1 to infinity. It's not continuous for anything over here because it doesn't even exist over here. Starts at 1, although you can't equal 1, and then goes for everything past that. Okie doke. Now, I think we're going to try just one more of these. Example 4. Then directions change one last time. Example 4. It has f of x equals cosine of x, and then g of x equals x squared. First thing I have to do, just like last time, is find the composite function. Find f of g of x. So take g of x, plug it into f of x. So this is going to say cosine of x squared. It's cosine of x squared. It's not cosine of x, the whole thing squared. It's just cosine of x squared. Now, we already kind of talked about cosine curves and sine curves yesterday, but it doesn't hurt to graph this just in case. Here we go, cosine of x squared. Here's my graph. Wow, kind of close together there. Oh, and then it starts to spread out in the middle, but I don't have a fraction to worry about in my function. I don't have a square root to worry about. I mean there's no asymptotes there. This is just a continuous curve that happens to get closer together the further out you go. So on this problem, I would say, here we go, I would say continuous everywhere. Or if you want to go back to use an interval, you would just say continuous on the interval, negative infinity to positive infinity. You could also say continuous everywhere. Okie doke. Now, last two examples here. We're kind of doing the same thing each time, but now it says, very specifically, to describe the intervals on which the function is continuous. Describe the intervals on which the function is continuous. We can't just say non-removable discontinuity at x equals 2 or removable discontinuity at x equals 0. Now it says specifically that we have to describe the intervals. So our answer is going to have to look more like this, where you've got parentheses or maybe brackets, depending on what function they give you. Okay, so example 5, I'm going to graph this without my graphing calculator. I don't think this is too bad here. F of x equals the square root of x minus 3. We know what a square root graph looks like. It has a starting point and it sprouts. This one has been shifted right 3. So it starts right here. Next point would be right 1 and up 1, and there we go. That's what f of x looks like. Now, to give the interval on which it's continuous, think about, first of all, where the function exists. It does not exist for anything over here. It starts existing where x is 3. Now, are we allowed to equal 3? Yeah, you could put a 3 right there. Square root of 0 is just 0. So since I can equal 3, I want to use a bracket, and it's going to be continuous for everything else past positive 3. So continuous on the interval 3 to infinity. Okay, always use parentheses with your infinities. Now, last one. This is not for the faint of heart here. Number 6. We're going to have a lot going on with number 6. And it says f of x equals x over x squared minus 4. X over x squared minus 4. If you want to go ahead and think about your suspicious x values, think about the x's that would make that 0. Add 4 to both sides, square root both sides. I'm concerned about positive 2 and negative 2. Now, since we're not trying to classify them as removable or non-removable, you might be able to just kind of take this and write out your intervals, but sometimes it does make a little bit more sense if you see it on a graph. So I'm going to still graph this anyway. I've got x divided by parentheses x squared minus 4. Now, we already know where the discontinuities are. -2, there's a vertical asymptote, and +2. So, because I'm not allowed to just say non-removable discontinuity at -2 and +2, that's not what the directions said. The directions want us to give intervals. So I'm going to have to start on the left side of my graph, because that's always where we start, kind of like a sentence. When you read a sentence, you go left to right. So I'm starting here, and I can tell that this graph is going to go all the way to the left. So why don't we start with -infinity all the way to right here. It stops being continuous at -2. And you are not allowed to equal -2, so you would need parentheses there. Now, once you get past the first vertical asymptote, it's continuous for everything else in between -2 and +2. So we're going to go back and use that little union symbol like we used a long time ago. And we're going to list all of our values between -2 and +2, but not equaling either one. Okay, and then the last interval, another union here, the last interval is from 2 to +infinity, but again, you're not really allowed to equal either of those. So parentheses everywhere. All right. I'm going to put the assignment up here. So with this assignment, pay attention to the directions. If it says just discuss the continuity, then you can just say removable, non-removable, whatever. If it wants an interval, just make sure you write it as an interval. So C24 from pages 96 to 97, we're going to do 33 to 36, 69 to 72, and then 77 to 79. We're all over the place. I want to say these last 3 problems must be intervals. On all the rest of them, you can write your answers a couple different ways, but you have to use intervals on the last 3 for sure. Here in a little bit, I've got quizzes to pass back. I meant to do it yesterday and I forgot, so remind me here in a little bit if I forget again.